In this video, I'd like to review how to find vertical asymptotes and then talk about how to evaluate limits at these vertical asymptotes. So just to recall here, vertical asymptotes occur at x values that only make the denominator equal to 0. So they only force the denominator to be 0. If both the numerator and the denominator are 0 instead, we have a whole. So if both the numerator and the denominator are 0 at a particular x value, we have a whole. But if we have only the denominator is 0 at that point, that is the location of a vertical asymptote. So here we're going to look at a bunch of different examples here. It says describe the behavior of the function at each 0 of the denominator. Use plus minus infinity when appropriate. At any vertical asymptotes, we want to find the left and the right hand limits. So here, my advice for these types of problems, and really for just about all of these problems, is to factor. If you can factor, it's going to help you if you do. So I think this problem is just going to be easier if we factor, so I'm going to do that wherever we can. Numerator, x minus 3, that cannot be factored. My denominator, though, two numbers that multiply to be 3, add to be negative 4, those would be negative 3 and negative 1, so x minus 3 and x minus 1. And now, first thing we want to do, it says describe the behavior at each 0 of the denominator. Well, I need to find the zeros of the denominator in order to do that. So I can take each factor here and just set it equal to 0. X minus 3 equals 0, x minus 1 equals 0. Here I have x equals 3. Here I have x equals 1. So those are the zeros. And I want to determine, is this the location of a whole, or is this the location of a vertical asymptote? And to tell, I'm going to look at those factors where they came from. So x equals 3, that came from x minus 3. If you have a factor of x minus 3 in both your numerator and your denominator, so I've got x minus 3 in my numerator and x minus 3 in my denominator, this is the location of a whole. Another way you can think about that is you can say, okay, if I can reduce this, right? If I reduce those factors, I'm left with 1 over x minus 1. If you cancel that factor out, that is then going to be the location of a whole. Anything that's left over after you reduce, or any factors that are only factors of the denominator, that is going to be the location of a vertical asymptote. So x equals 1, that is a vertical asymptote. So I found the zeros of the denominator, and I've started to talk about the behavior, but now it says, hey, I want to talk about the left and the right hand limits. I want to be able to evaluate these at this vertical asymptote x equals 1. So let's go ahead and do that over here. So I want to look at the limit as x approaches 1. Let's start from the left-hand side of f of x. And what we can do, we actually already simplified this function. We factored it and we reduced any common factors. If we wanted to, we can actually look at the limit as x approaches 1 from the left-hand side of this guy right here, of x minus 1. We can use that simplified version just to make our calculations a little bit easier. So, what do I know? I know that x equals 1 is the location of a vertical asymptote. So because it's the location of a vertical asymptote, I know that this left-hand limit, I really sort of have a 50-50 shot of guessing this. It's either positive infinity or it's negative infinity. It's one of those two. I just need to figure out which one it is. So what I'm going to do, you could graph this function, you could do this all sorts of ways. But what I'm going to do is I'm going to pick a number that's very close to 1 on the left-hand side here. So I'm going to think about, if I were to take x equals 0.9. I usually like to be within one decimal place. You could use 0.5. I would not use x equals 0. If you go one full unit away, I will say I think that's too far. So we want to be within one decimal place 0.9, 0.5, I think either of those would work here. And I'm going to plug this into this simplified version over here. I'm going to take 0.9 and I'm going to plug that in here and see what happens. Because I know my answer is either positive infinity or negative infinity. I just need to figure out which one. So if I have 1 over 0.9 minus 1, now we could go and do the math here if we wanted, but really all I'm interested in is the sign. Is it positive or is it negative? 1, that's in my numerator, well, that's a positive number, so I'm just going to put a little plus sign there. Divided by, in my denominator, 0.9 minus 1. You could say, okay, that's going to be negative 0.1, but again, the only thing I'm really interested in here is the sign. I know that's a negative value. A positive number divided by a negative number gives me a negative number. So I know at the end of all of this, I'm going to end up with a negative number, and probably a very large negative number. Here I should end up with negative 10 here, I believe. But because this is negative, this is going to be what tells me that this left-hand limit is, well, negative infinity, because when I took a number that was close to 1 on the left-hand side, I ended up with a negative value. And this is why it's so important that we pick a number that's very, very close to 1. If we pick a number like 0 or even negative 1, right, numbers that are too far away, we may not get the correct sign here. So we want to be within that 1 decimal place. We can evaluate the right-hand limit pretty much the same way here. Limit as x approaches 1 from the right-hand side of f of x. So we can use that simplified version. Limit as x approaches 1 from the right of 1 over x minus 1. So maybe this time let's do this. I'm going to pick a number that's very close to 1 on the right-hand side now. So I might pick, say, x equals 1.1, maybe 1.5, something along those lines. I'm going to plug that in and see, okay, do we get back a positive number? Do we get back a negative number? So 1 over 1.1 minus 1. Here I have 1 over, or rather 1, which is positive. Let's just put a plus sign there. 1.1 minus 1, I know when I subtract those two, I'll end up with a positive. I have a positive number divided by a positive number gives me another positive. So that's going to be what tells me, hey, this right-hand limit over here, this is what says, you know what, this right-hand limit is positive infinity. And that's all we really need to do to evaluate these limits. You can, again, look at the graphs. There's all sorts of different ways you can go about this, but I think this is probably the easiest way to do it, and I think I like this method because it does not require a graphing calculator. It doesn't require any sort of technology. If it's factorable, and most of the ones that we pick will be factorable, it should simplify pretty nicely. So let's look at the next example here. G of x, I have x squared plus 9x plus 20 over x squared plus 3x minus 10. Again, I'm going to start this problem just by factoring this. So let's see, I need two numbers that multiply to be 20, add to be 9. Those would be 4 and 5. So x plus 4, x plus 5. In my denominator, let's see, two numbers that multiply to be negative 10, add to be positive 3. Those should be, what, x plus 5 and x minus 2 here. So if I wanted to reduce, I could say, okay, x plus 5, those two cancel. I've got x plus 4 over x minus 2. So take that factor, x plus 5, set it equal to 0. At x equals negative 5, I have a whole. So there's 1 0 of the denominator. At x minus 2, that leftover 0 of the denominator, x minus 2 equals 0, x equals 2. This is the location of a vertical asymptote because it only makes the denominator equal to 0. Some students get really concerned. They say, well, what about x plus 4? What do we do with that? And I say, well, nothing, because we're not talking about zeros in the numerator. We're just talking about zeros of the denominator. If you did take x plus 4, set it equal to 0, that would tell you your x-intercept here for this particular graph, but that's neither here nor there. We're not particularly interested in that. So we've got the zeros of our denominator. We just want to look at the the one-sided limits at x equals 2. So let's look at the limits as x approaches 2 from the left-hand side, and we can use this simplified version of our function right here, x plus 4 over x minus 2. And maybe right below it here, I'm going to take a number that's close to 2 on the left-hand side. So maybe I might pick, how about 1.9 and plug this in. So 1.9 plus 4 divided by 1.9 minus 2. 1.9 plus 4, I get a positive number out of that. 1.9 minus 2, that's a negative number. Positive divided by a negative, well, that gives me a negative number, so I know that this limit must be negative infinity based on the results of plugging in x equals 1.9. For the right-hand limit as x approaches 2 from the right-hand side of x plus 4 over x minus 2. Here, again, I'm going to take the same approach, but this time I need a number that's close to 2 on the right-hand side. So I might pick x equals, say, 2.1 and plug that in. So here I've got 2.1 plus 4 divided by 2.1 minus 2. And again, I'm just checking the signs here. 2.1 plus 4, that's a positive number. 2.1 minus 2, that's another positive number. If I take two positive numbers and divide them, I'll get another positive number. That means that this must approach positive infinity on this side here. So very cool. Let's look at one more here before we wrap this video up. H of x here. H of x, I've got x minus 1 over 2 times x plus 3 quantity squared. So here in this case, this one's already factored for me. So hey, that's good news for us, less work for us to do. But that means if I look at this, I can't simplify this anymore. I'm just kind of stuck with this as it is. So I'm just going to take my denominator, set it equal to 0. 2 times x plus 3 quantity squared, set it equal to 0, so that I can find the zeros of the denominator. So I'm going to start by dividing by 2. That would give me x plus 3 squared equals 0 still. Maybe I take the square root of each side. That still gives me x plus 3 equals 0. So I only have one 0. It's x equals negative 3. And because that did not cancel, I know that this is the location of a vertical asymptote. If you're ever unsure, you can take that number, try plugging that back into your function. Here, I will end up with, negative 3 minus 1 gives me negative 4 divided by 0. So I know that when I look at this, I say, hey, I've got negative 4 over 0. This is the location of a vertical asymptote. So I know I need to look at the left and the right-hand limits now. So let's look at the limit as x approaches negative 3 from the left-hand side. And we've got x minus 1 all over 2 times x plus 3 quantity squared. Now here we are going to have to be careful because we're dealing with negative numbers, and being on the left and the right-hand side of negative numbers I think can be really tricky. If you need to, draw yourself out a little number line here. Here's negative 3. Well, if I'm on the left-hand side, a number that's less than that is, say, negative 4 or negative 5. So we want, say, negative 3.1. I think that would be a good choice of x value here. I'm going to take that number, plug that into my function, see, okay, do we get a positive or a negative number? So let's see, negative 3.1 minus 1 over 2 times negative 3.1 plus 3 squared. Negative 3.1 minus 1, I know that's a negative number, divided by 2. Negative 3.1 plus 3, that's going to be a negative number, but I want to square that negative number. So here this one's a little bit more involved. My numerator, that's not changing sign, it's still a negative. 2 times a negative number squared. So if I take a negative number times that same negative number, I know I'm going to get back a positive number. So let's see, I've got a negative. 2 times a positive number, that's going to be positive, gives me a negative end result. So this must approach negative infinity then. For the right-hand side, I want to look at the limit as x approaches negative 3 from the right-hand side of my function. And again, just refer to your number line over here. So numbers on the right-hand side, you're thinking about negative 2, negative 1. So I might pick a number that's very close here, maybe say negative 3.9, and I'm going to plug that into my function. So let's take x equals negative 3.9. Let's plug this in. Let's see if we get back a positive or a negative result. So negative 3.1 minus 1 over 2 times, hold on, I made a mistake. So see, it's very easy to make a mistake. Look at this right here. I said negative 3.9, but that's certainly not between negative 3 and positive 2. Excuse me, negative 3 and negative 2. Oh my goodness. This should be negative 2.9. So that is my mistake here. And just take that as a good illustration of why we should not be too careless with these problems. It's very, very easy to make a mistake. So x equals negative 2.9. Got negative 2.9 minus 1. 2 times negative 2.9 plus 3 squared. That's a little bit better. So negative 2.9 minus 1, my numerator I know will be negative. 2 negative 2.9 plus 3, I know that's a positive number, and I'm going to take that positive number and square it. So I have a negative here divided by 2. A positive number squared, that's really, say, a positive number times another positive number should give me another positive number, right? 2 times 2 is 4. Here I have a negative number divided by a positive, which gives me a negative end result, so this must approach negative infinity as well. So this is a really nice example because it does show that depending on the particular function, the left and the right hand limits are not always going to be different. It's really easy for students to fall into the trap of assuming that, well, if the left hand side approaches positive infinity, then the right hand side has to approach negative infinity. It's absolutely not the case. They can both approach negative infinity, or they might both approach positive infinity. You do have to go and do the legwork to show.